Today we are focusing on steady state monitoring and the very important, or we can say essential protocols for the irregularities control in our furnaces, in our blast furnaces. Now, our objective is to master the furnace's internal black box to ensure maximum campaign life and operational stability. As you must be knowing, these two parameters or these two activities are most important in order to run the blast furnaces in a stable manner and to obtain our basic objective of low cost hot metal. So to do that, we must first look at the macro level inputs that drive this reactor, and by doing this, we could able to obtain our those two basic objective, that is to maximize our campaign life and to have a operational stability, so that obviously both two things are complementary to each other in most of the time. So we can say that by doing one, the other objective is also getting obtained. Now coming to the macro synthesis, as you can see, the process is a continuous counter current exchange. We charge the burden, that is sinter, pellet, lump, and metallurgical coke at the top, while a preheated hot blast up to 1200 degrees centigrade and PCI are injected through the tuyeres. Now this create the rising gases and rising gases and descending solids. So solids and basically these solids gets melted in the bottom part, which are required to drain as a hot metal and slag from the hearth. So this is what about the macro synthesis of blast furnace. Now coming to the our next slide, which is about the structural anatomy of the furnace. As you can see, the physical shell is designed to manage this exchange, and from the parallel side throat for impact management to the conical Bosh that handle burden fusion and extreme heat. Now, this structural design protect the hearth, a carbon-lined collection basin where our liquid products aggregate, and it's supposed to be one of the most important part of the furnace. Of course, the entire integral part is important, but hearth is important from this point of view, that the liquid final our objective of melting iron ore is getting collected in this hearth, and from here we is to take out at a regular interval of time to discharge the final output. Now coming to the our next slide, which is about the internal zonal um, movements of the inside the furnace. And as you can see, the internal zonal moving inside the shell, we see distinct zone, the lumpy zone for the pre-reduction, the cohesive zone where the iron ore form viscous donuts, and the active coke zone where liquids drip through a solid coke matrix towards the raceway. Now, this stability of this zone is dictated by the balance of forces, and understanding of these dynamics is very important for all blast furnace operators. Now, as you can see, the forces in equilibrium is being shown in this slide, and this is a very important one. We track the delta P equations, as you must be knowing. It is the blast pressure minus top pressure, and the furnace only descend when the downward weight of the burden exceed the upward resistance of the blast pressure and liquid buoyancy, as it is shown. A spike in delta P is a critical warning, and it means the stock line has halted in most of the time. So it is a very clear and demarcation indicators in our operation of the furnaces. So monitoring of this delta P and timely combating to make it stable is one of the most important prerequisite for all blast furnace operators. Coming to the thermal gradient and gas reduction, this force balance is fueled by the thermal gradient. Now rising carbon monoxide and hydrogen gases strip oxygen from the ore, as we all know, moving from indirect reduction in stack to endothermic direct reduction in the Bosh. So this entire cycles begins in the raceway where the blast oxygen burned the coke at temperature up to 2250 to 2300 degrees centigrade. And now we also come across the burden permeability and the trick of the fines, which are one of the very important aspects that is to look into, as we have seen already earlier presentation where Aragon equations is shown that how a teeny fines could able to contribute delta P immensely high, and if he could not able to stabilize those delta P timely, then fines generation in the furnace will automatically keep on increasing, which will have a detrimental effect right from a scab accretion to dead man choking. So for these gases to ascend efficiently, permeability is our lifeblood, and without these, nothing, all adverse things started generating from here. So metallurgical coke, which are 45 to 50 mm and which are coarser, uh, act as our primary gas distributor. But fines under 6 mm are a constant threat, and as we can able to also see in the Biswas that fines curve, that after this 5 6 5 and 6 mm fines, our pressure increases tremendously, shot up straight. So this is a segment where a maximum threat to furnace is there, and all operators need to be extremely focused on these segments. So fines from poor screening or low CSR coke plug the voids, choking the gas flow and initiating a cascades of failure. And most importantly, that we have to understand that fines of this granulometry is contributing a different preferential segregation, especially in coke and ore, due to difference in their density. So we need to also take the fines as a not only about a geometrical dimension, it is about also a physical characteristics. We have to see how this different density segregate in the blast furnace in a different way. So that also become a complex issue in our furnaces. Now coming to the diagnostic dashboard. Uh, so when equilibrium fails, when permeability or thermal stability is disrupted, we face four major pathology and these need to be scrutinized very efficiently by each operators to bring back the furnace into normalcy, and there will be a minimum loss of production, productivity, and cost, and finally to equipment also. So, coming to our four pathological pillars, one is channeling, the second is scaffolding, the third is hanging sleeping, and fourth is the hearth coldness, coldness of the hearth, and finally, if timely action we cannot able to take, then it converted into a sort of a chill, which is really very adverse word for any blast furnace operators. Now, recognizing this telemetry shift early is the difference between a minor adjustment and a major furnace outrage. So, if we have a timely action, then things goes right. But if it become a sort of a stagnant sort of a thing, and over a day we could not able to improve, then things becomes major, and there we need to have a more losses, or in terms of unstable furnaces, frequency of a lot of fluctuation in the chemistry, the hot metal temperatures, and consequently a lot of fuel, because any inconsistency directly reflect the fuel efficiency. Now, coming to the pathology slides, or we can say the slides have a pathology activities. So, it's the number one, which is about channeling. So, as we know, channeling occurs when gas blasts through a path of least resistance, that is fluidizing fines. You will see a sharp rise in peripheral gas temperature and a sudden drop in top gas CO2. So these are the major indicators, and really a person must have to look into those trends carefully to analyze the furnace clearly, or your alarm system must gives us a feedback regarding these. So our immediate protocol is to open the slot to collapse the channel and reset the body distribution. Of course, this is not that straightforward. Definitely, in that sort of thing, temperature and pressure will also a guidance parameter, where it will show the operator that localized delta pressure tappings are also giving you a signals. So accordingly, you have to take action by reading all those things timely. Now, coming to the pathology 2, scaffolding and scap. If gas flow remains uneven, we risk the alkali cycle. Volatile potassium, sodium, and zinc evaporate in the Bosh and condense in the stack, gluing the body into the wall, as we all know, and the fundamental books is already corroborate these findings through a number of operational statistics of worldwide blast furnaces. So this scaffolding forces higher central velocities and require a extra cook charge to melt the incrustations. So these are the some way, and we need not to focus much more on that to otherwise this presentation will be further more lengthy. Coming to the pathology 3, which is hanging and slipping. As we know, a scaffold or high fines can cause the stock line to flatline, and this is a hanging, and when the supporting breeze finally fails, we get a slip characterized by a sudden drop in blast pressure. So massive slips are dangerous because they dump the cold material directly into the lower zone, and as we all know, the consequences which happens in terms of increase in direct reduction, increase in fuel rate, fluctuation in the chemistry, and a lot of heat dissipation in the hearth, which is ultimate dangerous approach. Now, coming to the pathology number 4, and which is exactly the heart choking, and chilling, and the most severe failure is the chilled hearth. As we have already talked about, this word is pretty very bad, and we need not to repronounce it again and again, because this is the ultimate disaster in the furnaces. So whether from a massive cold slip or a water leak or a liquid drainage, which drainage stops, and the iron slag freezes. So all these convert towards this situation about which we are talking, and this can bond the two-year also, and end a campaign prematurely also. So this is a very big happening of premature campaign failures. So we need to keep ourselves away from those words even, and we need to act fast. Mode our alarm system, diagnostic tools, our level 2 monitoring system should gauge these signals pretty well, and at the same time the operator should also put all his senses open to grasp these alarms earliest. So we fight this. So we can say that we have to fight all these emergency situations pretty well, and for this we have to combat action also, like we fight this with the emergency blank cook charges or increased blast temperatures too. Now coming to the master diagnostic matrix, and this matrix is your shift level cheat sheet, we can say. So it connects early warning signs like top temperature spikes or viscous slack to immediate countermeasure like reducing bean volume or altering the charging sequences, changing the orientation of BLTs, or gauging some changes with LMGs opening, discharge rates, portion changing, and so many permutation combination. But the thing is that after each changes, a person should track the consequences, the refreshing of the burden layers, and accordingly expected results is to be compared. So we can say that important thing is the action as well as its measurement are the best way. So uh, um, uh, but after all, we can say that the best way to handle these pathologies is to prevent them entirely. And coming to our next slide, as we are discussing more and our things becomes more lengthy. So coming to the operational imperative, we can say that the prevention at the top is the ultimate cure for the downstream failure, and is all about a proper modern preparation which sort out our most of the problems, because once it allow in the vessel, it travel downstream the vessel, it create a problem. So stability of the furnace is won or lost at a stockhouse only through the strict screening of the fines, stabilization of the coke, CSR, and moisture control. And adherence to these standards ensure a perfect stock line design and a steady state furnace.